So, in the previous lecture, we talked about the conversion of transfer function to state space, and it comprises of two cases. One case was already been discussed, which was if you had a constant in numerator of the transfer function, like we did the example given here. Today, we'll discuss the second case, which talks about the presence of a polynomial in the numerator. So, how are we going to obtain the state space representation of such systems? And thereby we'll obtain the state model of the transfer function given here. So suppose that you're given a transfer function having a polynomial in the numerator as well as denominator. So in problems of such type, what we do is we separate out the denominator and numerator in this manner, and then we try to find out the state model for the blocks separately. So we will try to first find the state model for this particular block, for this one first, and then we'll try to find the state model for the second block. So if you look at the first block, so the transfer function of the first block is given as, if we assume that the output from the first block is O and the input is R, then the transfer function is given by O by R, which is I guess 24 shouldn't be here. So this 24 wasn't supposed to be here. Alright, so this is 1. So the transfer function is given as O by R 1 upon S cube plus 9s square plus 26s plus 24. And if you apply the same principle or the same method that we did in the previous example, so we have to first cross multiply the functions. So what we get is S cube plus 9s square plus 26s plus 34 multiplied by O, which is equal to, this is R, 1 multiplied by R. And now if we take the Laplace inverse of this function, what we get is, and of course we are going to assume initial conditions to be 0 because we are dealing with transfer function and initial conditions in transfer function are taken as 0. And thus if you take inverse Laplace of the given function, what you get is d cube by dt cube of O, then you have 9d square by dt square of O, then 26d by dt of O plus 24O equal to 1R. Now if we assume state variables as x1 equal to O, x2 equal to O dot, x3 equal to O double dot. So what we get is x1 dot is equal to x2, x2 dot is equal to x3, and x3 is equal to minus 24 x1. So you assumed O as x1, O dot as x2, and O double dot as x3. And thus what you get here is minus 24 x1 minus 26 x2 minus 9 x3 plus 1R. So this is 1. And you have the output O, which is equal to x1. So if you implement this state equations and the output equation in the form of state model, what you get is a model shown over here. So this is very similar to the question that we did in the previous example, except for the numerator that in this case has 1 instead of 24. So what we have is RT fed to the comparator and all the other blocks connected using these equations. So because this was already discussed in the previous lecture, how to connect blocks and how to obtain the different state variables by putting integrator in their intermediate. So I guess it's not important to discuss it again. And if you have any doubt of connections of these blocks, how they are connected, then you can refer to my previous lecture. So this is the block state model representation of the given state equations and the output equation, but it's not final because what we did was we obtained the state model for this particular block, but we still have to acquire the state model for this block. So in order to obtain the state model for the second block, we assume the output as C and the input to this block as x1, since we saw here that the output O was equal to x1. So we directly feed this x1 as input to the second block. So C by x1 is nothing but the transfer function of the block, which is s squared plus 7s plus 2. And similarly, if we cross multiply, then what we get is C is equal to x1 multiplied by the numerator, the polynomial s squared plus 7s plus 2. And if you take the Laplace inverse of this, assuming initial conditions to be 0, we get a time domain transformed function C, which is equal to x1 double dot plus 7x1 dot plus 2x1. And again, we have already assumed the state variables. We have taken state variables as x1 dot equal to x2 and x2 dot equal to x3 and x3 dot this function and O is x1 in the previous slide. So we get here is as x1 dot as x2 and x1 double dot as x3. Since x1 double dot is equal to x2 dot, while x2 dot from here is equal to x3, and that is why we get x2 dot equal to x3, which is nothing but x1 double dot. So we did this because we are trying to obtain the output C in terms of state variables. X1 is already a state variable. X1 dot is not a state variable, rather a state change. So we'll convert the state change into state variable, and since we knew that x1 dot is equal to x2, and that is why we are going to substitute x1 dot by x2, and likewise x1 double dot is a state change and not a state variable, and thus we'll be substituting this by a state variable x3. So we do this in order to obtain the output variable C in terms of either the state variables or the input U, because if you remember that y, which is output here as C, was given by Cx plus du. So if you look at this expression, what we see is that y should be either written in terms of x or u. There should not be any state change like x dot in this expression, and thus we try to change this equation finally into this form. So what we get is y equal to C, which is nothing but x3 plus 7x2 plus 2x1. So this is the required output equation. Now we will try to implement this equation into state model, and this can be easily done since we know that x1 and x2 has a relation with an intermediate integrator. So if you have an integrator between x1 and x2, since x2 is nothing but x1 dot, so this point is nothing but x1 dot. So if you integrate x1 dot, what you get is x1. Likewise, this is x2 dot. So if you integrate x2 dot, what you get is x2, and again integrating x2 will give you x1. And now in order to connect this out, in order to obtain output y, which is nothing but x3, so you are going to pick a signal x3 from this point. So you pick the signal x3, multiplied this by again 1, and give it to the comparator with a plus sign. Then you have 7x2, which will be picked from the point x2 multiplied by again 7 fed to the comparator. Then you have 2x1, so you are going to pick the signal from x1, multiply this by again 2, and then going to feed this to the comparator in order to obtain the final output y. Now since you know that x3, so this is the block representation, the state model representation of this block, and you already obtained the state model for this block in the previous slide. So what now you're going to do is you're going to connect the two blocks in such a manner. So this block, let's call this as B1, block 1, and this as B2. So you'll be connecting this intuitively such that you get the final state model representation of the system. And we see that here in this block we have these expressions already given, which are same to the block representation which is given here. So we simply are going to pick these, or we are going to place these blocks, these blocks, which is x3, x2, x1. So you see, if you look at this block, you see that x3 is here, x2 is here, and x1 is here. So they are the same blocks, and we are going to connect the we are going to provide those connections in the second block at this point in this manner. So the final block representation would look something like this. So this came from the block 1, while we obtain this part from block 2, and we connected them in order to obtain the final state model representation of the given system, given transfer function. So I guess this is clear to all, and if you have query and doubt, you can ask me. Now we talk about conversion of state space to a transfer function. So in the previous part, we talked about conversion of transfer function into state model. Here we'll talk about conversion of state space into transfer function. So let us assume that we are given a system having a state equation as x dot equal to ax plus bu, and the output equation is y equal to cx plus du, and this is nothing but the general form of state space representation of any system. So in order to find the transfer function from these equations, what we do is first we assume initial conditions to be 0, since this is again something inherent to transfer function, that initial conditions are always taken as 0. And taking the Laplace transform of these two equations, the state equation and the output equation, what we get is s times of xs, which is Laplace transformation of x dot, which is equal to axs plus bus, and then from output equation you get as ys equal to cxs plus dus. Now in order to make things simpler, we are going to drop the terms terms of s within the brackets. So equation 1 can be written as si minus ax. So if you're going to take this term on the left hand side, what you get is sx minus ax, and from that you get an expression si minus a, where I is nothing but the identity matrix. This is an identity matrix, and the order of this matrix will be judged by the size of a. So the order of a will decide the order of I. So if suppose that matrix A is a 2 cross 2 matrix. So if this is a 2 cross 2 matrix, in that case you're going to take this identity matrix as 2 cross 2. And if A is of the order 3 cross 3, then in that case you're going to take the order of I as 3 cross 3. So you get si minus a multiplied by x, which is equal to b times u from equation 1. And if you further simplify this, you get x is equal to si minus a inverse into bu. So this is matrix operation that you already know about, and you know how matrices are being dealt, how you deal with matrices, how you multiply and divide them. So, and you should be careful in writing expressions of such type, because if you, instead of writing b si minus a inverse multiplied by bu, if you wrote this as bu and si minus a inverse, then this will be incorrect. So the answer that you get from this will be incorrect. So this is wrong. So you know how to multiply and divide matrices and what order are they're going to be operated. Now if you substitute the value of x in equation 2, which is y equal to cx plus du. So if you're going to substitute this value of x si minus a inverse bu at this location, at this place, you get y is equal to c si minus a inverse bu plus du from equation 2. Now this can further be written as, if you take u as common, so what you get is this expression multiplied by u, And this matrix CSI minus A inverse B plus D is called a transfer function matrix, because the transfer function is now obtained by the output y divided by input u, which is giving you a term CSI minus A inverse B plus D. So this is the expression for finding the transfer function if state model of a system is already given. So let's try to understand this using an example. Suppose that a system is given by the following state variable representation and you're required to find the transfer function. So it's given here as x dot equal to ax plus bu and y is equal to cx plus du. And thus it's clear that you can identify the matrices. So this particular matrix is A, while this matrix is B, and this matrix is C, while D is 0. And since we know that the transfer function is given by y upon c equal to c s I minus A inverse B plus D, so since we identified C, A, B and D, now we are going to evaluate Si minus A inverse. So before finding the inverse of a matrix Si minus A, we will first evaluate Si minus A. So in this case, the matrix A is a 3 cross 3 matrix, and thus we are going to assume identity matrix to be a 3 cross 3. So S multiplied by identity matrix of order 3 cross 3 minus A is written here. And if you simplify this, you get this matrix, which is given here. And this gives Si minus A inverse, which is given by an expression adjoint of Si minus A upon determinant of Si minus A. And I assume that you all know about this as well. So any matrix, let's say if you're given a matrix X and you're required to find the inverse of this matrix, we all know that this is equal to adjoint of that matrix divided by inverse. Sorry, divided by the determinant of the matrix X. So now how do you find adjoint of any matrix? Suppose you're given Si minus A, this is Si minus A matrix, and to find the adjoint of Si minus A, if you remember correctly, so it was the adjoint of a matrix was given by the transpose of its cofactor matrix. So in order to find the adjoint of Si minus A, you'll first have to find the cofactor of Si minus A, then you'll have to take transpose of it. So in order to obtain the cofactor of this matrix Si minus A, if you can remember correctly that we wrote the element wise cofactor matrix. For example, if we want to find C11, which means that in this case, since cofactor matrix is also be going to be of the order 3 cross 3, having elements C11, C12, C13, then you have C21, C22, C23. Then third row is C31, C32, and then C33. So in order to find the first element C11, what you did was you had a formula which is minus 1 to the power 1 plus 1, and then you, for this finding the first element, you took this matrix, that is determinant of S minus 1 to S plus 3. So this will give you the first element of the cofactor matrix C11. And likewise, if you were supposed to find the element C12, then for this you had formula minus 1 to the power 1 plus 2, and determinant for the matrix if you're going to leave the corresponding row and column. So if you're going to leave the first row, since you're talking about C1, 2, so the first row and the second column. So first row is this, the first row is this, and the second column is this. So if you're going to leave this column and rows, so what you're left is with the matrix comprising of elements 0, 1 and minus 1 s plus 3. And you're going to write this matrix in the determinant form here. So this will give you the value of C12, which is written in matrix C here. So if you evaluate this, what you get for C11 is minus 1 to the power 2 is plus 1, s into s square plus 3s minus 1 plus minus 1 into plus 2, which gives you plus 2. So you get element s square plus 3s plus 2 as the first element C11. While C12, you'll obtain this as minus 1 to the power 3 is minus 1. Now here if you look at the determinant, this is s plus 3 multiplied by 0 is 0. 1 into minus 1 is minus 1, and you will be having a minus sign here. So minus 1 into plus 1 is minus 1. So this will correspond to C12. Likewise, you will be having C13, which will be minus 1 to the power 1 plus 3, which is again plus 1. And then you're going to leave the first row and the third column in this matrix. So if you leave the first row and the third column in this matrix, you will be left with elements or the matrix 0, s, 1 and 2. And the determinant of this matrix will be minus s, and thus you will get C13 as minus s. And after substituting all these values in the cofactor matrix, you are going to take the transpose of it. Since adjoint of any matrix is equal to the transpose of its cofactor matrix, and thus if you see in this matrix, if you look at this matrix, you're going to have the components C11 as here, and after taking transpose, the element which was taken as minus 1 as C12 was taken as minus 1. So if you take the transpose of it, this will come into the first column and second row. Likewise, C13 which was equal to minus s, after taking transpose will take this location corresponding to the first row and first column and third row. So I guess this is clear. So after taking adjoint of Si minus A, you get this matrix, and you're going to divide this by the determinant of Si minus A. So the determinant of this matrix comes out to be equal to the polynomial s cube plus 3s square plus 2s plus 1. And since we know that the transfer function is given by Csi minus A inverse B plus D, and if we are going to substitute all the values, since we identified C as 1 0 0, A as this matrix, B as 10 0 0, and D was 0. So if you substitute each of these matrices into the formula, which is Csi minus A inverse B plus D, and C is 1 0 0, then you have Si minus A inverse, which is nothing but this expression, and you substitute it here. Then B was identified as 10 0 0, and D was 0. And if you again multiply each of these terms, you get the final transfer function given here. So this is the required transfer function of the system, which was represented by the state model or state space representation. So I guess this is clear to all, and if any one of you have any query in finding the transfer function from state model or finding the state model from a given transfer function, you can ask me.